There's one more topic we should talk about while we're talking about electric fields. Let's talk about these electric field lines again. Remember how the lines go radially out away from our electric charge like this? And remember how the electric field is stronger closer to the charge? So my electric field is strong here, getting a little weaker, and then weakest out here around the outside. The electric field is always strongest near the charge and weaker as you get away, but remember that the electric field is the charge divided by 4 pi epsilon distance squared. Oops, right here, distance squared. So as the distance increases, that means that the electric field always decreases. And as the permittivity increases, that also means that the electric field decreases. So this means that if I had a given charge, that the electric field in air, which has an epsilon r of 1, is going to always, always, always be greater than the electric field in any other material, such as water, which has an epsilon r of 80. Magnitude of these electric fields. The direction is going to stay the same. But sometimes it's useful for us to just describe the density of the lines that you see here in this picture, these arrows. So we use another variable. The variable that we use is called electric flux, or electric flux density. A flux is just something that's moving, or a flux line. This is a flux line. Here's another flux line. Each of these arrows is a flux line. So the electric flux density is given by D. It is a vector, and it is epsilon times E. So the electric flux is proportional to the charge, inversely proportional to 4 pi and the distance squared. The epsilon value, this epsilon value, has been normalized out. This means that the density of the field lines, or the shape of the density of the flux lines or the shape of the flux lines is the same regardless of the material that you are in. So the electric flux in air is equal to the electric flux in water.